This is recording for Edexcel Further Pure 1, Coordinate Systems, Section 2.6, Tangents and Normals to an Ellipse. Well, this method of finding tangents and normals you should be very familiar with now. The idea that we can calculate using calculus the value of the gradient of the tangent mt, so that will be f dashed x1, the value of the gradient at the point that we're considering, and then using the straight line equation y minus y1 is equal to gradient x minus x1. Similarly, for the normal, we simply have, instead of the gradient of the tangent, the gradient of the normal, where because tangent and normal are perpendicular to each other, we have the gradient of the normal is -1 over gradient of tangent. So really that is very familiar work, and all we need to do is to consider how we calculate the derivatives of the function. Two different ways to consider the equation, Cartesian equation x squared over a squared plus y squared over b squared equal to 1. Well, you could rearrange it to give y equals, but much more straightforward that is to use implicit differentiation. If you haven't covered implicit differentiation yet in your course, it might be wise to wait until you have. However, let's go through the result. Differentiating both sides with respect to x, we get 2x over a squared plus 2y over b squared, and then dy by dx. And on the right hand side, the derivative of 1 is 0. So rearranging that gives dy by dx is equal to negative b squared x divided by a squared y. An alternative method is to use parametric differentiation, so we have the parameters for the ellipse x equals a cos t and y equal to b sine t. So there's the derivative, x equal to a cos t gives dx by dt is equal to negative a sine t. If y is equal to b sine t, then that gives us dy by dt is equal to b cos t. And then dy by dx is equal to dy by dt divided by dx by dt. So that is negative b cos t divided by a sine t. So that gives us a gradient of negative b cos t over a sine t for the tangent. The gradient of the normal is then -1 over that. So perhaps worth pausing the video at this stage and just checking through this page to make sure you understand fully where they come from. You might also like to consider how these two results correspond to each other, because they should be giving obviously the same value for the gradient. Also, it's worth pointing out that these methods can be used to calculate the gradients of the parabola that you looked at for AS level but weren't expecting or expected to be able to produce the result yourself. For A level, then now that you can use implicit differentiation, parametric differentiation, then you should be able to produce a similar result for the parabola. The intention is not that you learn this as a result, but that you know how to prove or to find the gradients of the tangent and normal to an ellipse. And once we've got these gradients, finding the equation of the tangent and the normal is very, very straightforward. So we're simply substituting this value for the gradient into the expression for the tangent, which is a straight line, and then rearranging. So again, I'd like you to pause this video and just check through this line of working. As I say, it is not intended that you learn this result. It's the method which is important. So here's a question then that is similar to an A-level style question. It says we have an ellipse and it's shown on the diagram, has equation x squared over 9 plus y squared over 4 equal to 1, and we're asked to find the equation of the tangent at the point 3 cos t, 2 sin t. So that is at a cos t and b sin t. In other words, a general point. Once we've done that, we want to find the coordinates where the tangent meets the axis. So we've got the equation, and to meet the axis we simply set at this point here we have y equal to 0, and at this point here we'll have x equal to 0 to find the coordinates of those points. And then we're asked to show that the area of the triangle produced by those points and the origin, this one here, is equal to 6 cosec 2t. So the first part of the question is going to be that standard bit of differentiation to work out the equation of the tangent having got its derivative to give us the gradient, and then using that equation to find the points, and then straightforward little bit of calculation of area, but just note we've got to get it into this particular form. So here's our expression, and we're asked to look at the point P, which is equal to x is 3 cos t and y is equal to 2 sin t. The first one means that dx by dt will be equal to negative 3 sin t, and the second one gives us dy by dt is equal to 2 cos t, and then dividing those, dy by dx gives us negative 2 cos t divided by 3 sin t. So the tangent will then have equation y minus y1, so that's y minus 2 sin t is equal to the gradient, which is negative 2 cos t divided by 3 sin t, multiplied by x minus x1, which is x minus 3 cos t. So there it is written out again. Just again pause, make sure that you can get that result, and then finally it has been tidied up to give us this expression: 2x cos t plus 3y sin t is equal to 6. Well, the next part of the question asks us to find the points where it crosses the axis, so that setting first of all y equal to 0 for this point and x equal to 0 for this point, we can see that x equal to 0 gives us a value of y is equal to 6 over 3 sin t, which is 2 over sin t, and similarly y equal to 0 will give us x is equal to 3 over cos t. so that the coordinates on the axes, m on the x-axis is at 3 over cos t, so that's 3 sec t 0, and n is at, on the y-axis, so it's 0 and 2 over sine t, so that's 2 cosec t. And given the results for x and y, it's then straightforward for us to be able to calculate the area of the triangle. So we have here half base times height. So 6 over sine 2t, and writing it in the form that's expected, 6 cosec 2t. That's the end of this video. In the next one we'll be looking at tangents and normals to hyperbole.